Hello, everyone. So today we're going to be getting into the last part of chapter 11 before we move on to chapter 9, and chapter 12, and we're going to be continuing to work on our theme of bringing it all together, seeing what the point of these things we've been learning has been. So up until now, despite how complicated things have been, we have still fundamentally been looking at ways to simplify expressions. Remember the difference between an expression and an equation? An expression is exactly that. It's just a statement, and there's not much I can do with it by itself. You could think of 6 as an expression, even though it's just a number as well. 3x plus 12, that's also an expression. 6x squared plus 24x plus 19, that is an expression because I have ultimately no idea what those missing variables could represent. They could be anything. But if I suddenly introduce the equal sign in there, that's when it turns into an equation, something like 4x plus 6 is equal to 10. That is an equation. It is a full mathematical sentence because now there is a clear and definite answer to that missing variable that I can find. And that is ultimately the objective here. How do we find these missing pieces, these missing values based on what we know? We do that by turning expressions into equations. Now, up until now, we've basically been looking at ways of simplifying very complicated looking expressions. Why do we do this? The reason will start to become more apparent in today's video and in the subsequent ones, where we have these very complicated looking expressions. Just by looking at them, it seems like there's no way we could solve these. Like, how in the world are we supposed to find what missing variable makes that value, makes that true? But when we simplify the expression part of it a little bit, we find out, well, this thing that looks very complicated to solve really isn't as complicated as it looks. There's ways we can simplify it and make it much easier to solve. We always take our classic approach of taking a hard problem and reducing it to an easy problem. To do this, let's look at a couple of examples here. Let's say, for example, that I had x squared plus 6x plus 9 divided by x squared plus 7x plus 12, and I told you that is equal to 2. And here is the question ultimately. The question is, x is equal to what? So here is my classic algebra approach. I have given you an equation here. This is a full mathematical sentence which tells me that this unknown quantity squared plus 6 times that same quantity plus 9, all divided by the quantity squared plus 7 times the quantity plus 12, would be the same thing as 2. That's how I state it in English. Does that sound complicated to you in English? I agree. It sounds very complicated, and it sounds even more complicated to mathematically try to solve this. How in the world am I going to figure out what missing variable makes this statement true right here? Now, as I'm given it, it is very difficult to attempt to solve this. It's not impossible, but it sure would be difficult and time-consuming. But I happen to notice that if I could just simplify this and make it a little easier to work with, then I might be able to find my answer with little to no trouble. So how do we go about simplifying quadratics? That's right, we go about factoring. So let's factor both the top and the bottom of this fraction. If I factor them both, so if I factor my numerator, I'm going to get x and x. I have positives all around, so I'll put positives all around. So what two numbers multiply to give me 9, add to give me 6? That's going to be 3 and 3. When I factor my denominator, again, x and x, I have positive and positive. What two numbers multiply to give me 12 and add to give me 7? That's going to be 4 and 3. So I'll always continue to write the other sign of the equal sign. So this expression really could be thought of as this expression. And I happen to notice when I do that, I have an x plus 3 divided by an x plus 3, so these cancel. So now I can say this is really the same thing as x plus 3 divided by x plus 4 is equal to 2. So this equation right here is logically equivalent to this equation right here. I can work with either one I want because at the end of the day, they're exactly the same thing. Just by looking at them at a glance, I'd much rather work with this. Seems a lot easier to work with. So now how am I going to go about solving this right here? Well, I need to clear out my fraction here. Remember how we would do that if we had this fraction from earlier in the year? Let's say I had 3x over 2 is equal to 6. How would I go about solving this? That's right, I need to get rid of this fraction right here. Well, if I'm dividing by 2, how do I undo that? I undo that by simply multiplying by 2. Then those will cancel, but to preserve equality, I must do the same thing to this side. So I could say 3x plus 6 is equal to 12, and then of course I could solve by saying x is equal to 12 divided by 3, which is just 4. So I need to apply the same logic here. If I am dividing by x plus 4, well, how do I undo that division? What's the opposite of division? Multiplication. So I'm going to multiply times x plus 4. Multiplying and dividing by the same thing simply cancel each other out, but to preserve equality, I need to multiply this times x plus 4. So on the left side, all I'm left with is x plus 3. 2 times x is a 2x. 2 times 4 is 8. All I've done is distributed that 2 among these terms. So now I have reduced this complicated looking equation to this much easier equation to work with. And this looks a lot more like what we've been working with all this time. So how do I go about solving this equation? I need to get my variables together and my numbers together. So I'll get my variables on the left, my numbers on the right. Excuse me. So if I do that, I need to get my variables over here. So I will subtract this 2x, but I must do that from over here as well. And I will subtract this 3 and subtract it from here as well. So 1x minus 2x is negative x. These will cancel, and of course these will cancel as well. And 8 minus 3 is positive 5. So the opposite of x is 5. That of course tells me x must be negative 5. And here's my answer. So my conclusion is, with this original question, what unknown value makes all of this the same thing as 2? The answer is negative 5 makes that true. As always, the beauty of this is I can double check my answer. I can prove I'm right or wrong. So let's double check that. Let's assume x really is equal to negative 5. So if I replace every x with a negative 5, then I have negative 5 squared plus 6 times negative 5 plus 9 divided by negative 5 squared plus 7 times negative 5 plus 12. And let's see if that really does give me 2 the way I think it will be. So negative 5 squared is 25. 6 times negative 5 is negative 30 plus 9. Negative 5 squared is again 25. 7 times negative 5 is negative 35. And then I have plus 12. So 25 minus 30 is negative 5, plus 9 is positive 4. 25 minus 35 is negative 10, plus 12 is positive 2. And lo and behold, 4 divided by 2 does indeed equal 2. So my answer is right. When you plug in a negative 5, you will indeed get 2 here. So I hope this is starting to make a little more sense now as to how we apply these techniques. As it is given, we could not solve an equation like this. We don't really possess the methodologies to do so. But when we simplify things a little, utilizing the techniques we've been learning, we realize, well, this really hard-looking equation really isn't hard at all. It reduces to this much simpler equation that we've known how to solve since the early part of this year. So always try to take your hard problems and reduce them to easier problems. Let's take a look at another example or two. So let's say we had this example for starters. What if I were to give you 7 over x minus 3 plus 4 over 3 minus x and say that that is equal to 1, for instance? So this time I am adding two fractions together instead of giving you one whole fraction. It has a variable in there, and there is an equal sign. Equal sign means equation. A variable in there means that I can solve for that variable because I am relating this quantity here, which is not known, to something that is known. The question is, of course, x is equal to what? What unknown value would make this statement true? That if I took 7 divided by the unknown minus 3 plus 4 divided by 3 minus the unknown, I would get 1. What makes that statement true is the question. So how are we going to go about solving this? Well, once again, this looks too complicated to solve as it is. I don't like having fractions, and I don't like having two fractions with the same variable in it. This is just not something I can work with. I need to get rid of these fractions ultimately, if at all possible, and reduce this hard-looking equation to something that is much easier to solve. So how am I going to go about this right here? I notice, however, that this right here, 3 minus x, is just the negative of x minus 3. It's the opposite of it. If I distribute this negative, negative x, and negative of negative 3 becomes positive. So I could write this fraction like this, 4 over negative x minus 3 is equal to 1. But remember, a negative sign right here at any point in the fraction can be pulled out of here because it can be thought of as negative 1 times this whole thing. So I could really rewrite this, I'll move up here, as 7 over x minus 3 minus 4 over x minus 3, and say that that is equal to 1. All I've done is I've taken this negative sign and replaced that plus sign with it. So if I do that, I have a common denominator here. These are the same type of fraction, so this really becomes 7 minus 4 all divided by x minus 3 is equal to 1, because now they're on the same terms. I've gotten them on the same terms. So 7 minus 4 is, of course, 3. I have 3 over x minus 3 is equal to 1. Now this already looks a lot easier to work with than this did right here. So how am I going to undo this fraction? I have 3 divided by x minus 3. How do I undo division? I undo it by multiplication. So I'm going to multiply by x minus 3, then those will cancel, and all I'm left with is a 3. But if I do that to preserve equality, I have to multiply this times x minus 3. 1 times x minus 3 is just x minus 3. So I have x minus 3 is equal to 3. How do I undo that subtraction? I'm going to add, and I end up getting 6 is equal to x. I could write this in any order I want. When two things are equal, it doesn't matter. And the conclusion I come to is that x must be 6. Let's double check that we're right. If I plug in a 6, 6 minus 3 is going to be 3, so that fraction becomes 7/3. Plus 4 over 3 minus 6 would be a negative 3. Now, once again, this negative right here at any point in the fraction can be factored out, so this really becomes 7/3 minus 4/3. 7 of them minus 4 of them is 3 of them. So I have 3/3, and 3 divided by 3 is indeed equal to 1. So we're correct. Starting to make a little more sense how we utilize some of these techniques. We can't solve this equation directly, but if we apply some of these techniques to simplify things a little, then we can solve it. That's the objective here. The objective is always to be able to solve an equation, to find something you don't know that you would like to know, and finding the easiest way of doing so. Let's take a look at one last example here, which is a little more complex. What if we had 3 divided by x plus 5 divided by 6, and set that equal to 1 over 4x. So this time you'll notice We have a fraction without a variable. We have a variable now on both sides of the equation. So how are we going to go about solving something like this? What unknown value makes all this true right here? So we're left in a bit of a quandary right here. We have fractions on both sides of the equation, and also these do not have a common denominator, so I can't simply add them as it is. I really need to get these three things on the same terms. It's like I have nickels here, dimes here, and pennies here. It's just these things simply cannot speak to each other. So trying to find out which one is which is going to be almost a hopeless task. I really need to get these on the same terms. So you remember the technique we learned for finding a common denominator for all things? We find the least common multiple of these denominators right here. So I'm going to break it into two pieces. I need the least common multiple of the numbers and the least common multiple of the variables. So the numbers I have are 1, 4, and 6. That 1 is just kind of understood. I have 1, 4, and 6. And the variables I have are just x and x. I have an x here and I have an x here. So what is the least common multiple of 4 and 6? That's going to be 12. I don't even need to worry about the 1. And what is the least common multiple of x and x? Well, that's no trouble. It's just x right there. So in order to get rid of my fractions and get these on the same terms, I'm going to multiply both sides of the equation by the least common multiple, 12x. So I'm just going to rewrite the left side of my equation times 12x, but once again, to preserve equality, I must do the same thing over here. So when I do that right here, when I distribute this 12x, so 12x times 3 is 36x. 12x times 5, 12 times 5 is 60. So I have 60x divided by 6. And lastly, 1 times 12x is just 12x. Now at a glance, it doesn't look like I've simplified things a little. I still have all these fractions, but that's about to go away. And that's the objective right here, is to get these set up to where all of the fractions will simply cancel out, because x divided by x, those cancel. 60 divided by 6, that cancels and leaves me with a 10 here. And 12 divided by 4, those cancel and leaves me with a 3 here. And my x cancel completely. So I'm left with 36 plus 10x is equal to 3. And this is going to become my equation. So in other words, this equation right here, and it is an equation, remember that, is logically equivalent to this equation right here. Ultimately, these are two different sentences in a language that say the same thing. They're stated differently, they look different, but they're not really different. How many times am I going to end up saying that this year? These two things look different. I think everybody would agree with that. I agree, they look different, but ultimately, they're not really different at all. They state the exact same thing. So if they are not different, that means I can choose to work with whichever one I want. Which one would you rather attempt to solve, this or this? I agree. This is much easier to solve. So how am I going to go about solving this? So I have 36 plus 10x is equal to 3. So first I'm going to subtract my 36. And I get 10x is equal to negative 33. And when I divide both sides by 10, I'm going to conclude x is equal to negative 3.3. Who would have thought that by looking at that complicated equation and even seeing a complicated answer with a decimal, that we could have solved it like that? But as you see, using just a few simplification techniques, your least common multiple, and canceling things out, we were able to take a hard problem and make it into a pretty easy problem to work with. So we're going to be practicing these over the next coming days right here. Don't be intimidated if you don't get this on the first try. There will be a few more videos on this, but I encourage you, practice, practice, practice. I'll be posting some practice problems and assignments on this. And as usual, always feel free to let me know if you have any questions. I'm very happy to help. God bless you all and thank you.